Okay, welcome everyone back our lesson. So today lesson we will mention one of phenomenon that guy very famous state is called the phase. Or I remember that it have the other name is called the phase kickback. Yeah, that is one of the how we have to the entangle attangment the qubit, and we make a kind of transform the state, the qubit state. So that's why we need to snapshot. That's because we need to capture the snapshot for the phase kickback or the phase and see how the qubit state transform, and we can see how the quantum system maybe can solve this kind of problem. So this is one of the part for the introduction to the quantum computing and programming. Okay, so first time we can look to see what is phase disk or what is phase kickback. Okay, first is if you see when we have a kind of phase difference, yeah, okay, exhibit you can represent in two parts. It's this kind of this qubit 0 and qubit 1, right? So we can have a two state 0 and 1 at the same time. So you can change full to the state of matrix. And over here is the P is kind of probability for state 1, and the phi this kind of quantum phase between the qubit 0 and qubit 1. So if you remember, this one have Euler formula. Yeah, Euler formula. We can calculate about the exponent I phi, right? And because we can have a transform, we have two entangles, the qubits 1 and 0. We have the qubit move on the Q sphere, so they can maybe make a transform or kickback. So okay, we have the qubits entangled together. So the probability for one qubit, for example, the qubit 1 can picture or can snapshot maybe about 70%. Yeah, this one. This is about 70%. So this area can help you to understand. Okay, this kind of 70, because some in simulation. Simulation we do not see this part. Okay, this part we create by ourselves to simulate, but in practice maybe you only need you can see this part. But when you see this kind of circle and with blue color, you can understand it's a kind of near with this one total 100%, and use this part, so it's kind of total about 70%. So this blue can represent probability for the qubit 1, and the rest is the qubit 0. Yeah, and when with the quantum phase, the chain, and you can take a snapshot or take a picture of you can capture, and you can capture state. For example, when the the quantum state move, yeah. This one a kind of a half of circle, one quarter of circle. So you can see the road counterclockwise center point. This kind of 90 degree. So this is similar like this. Yeah. But if you see over here is a sphere. Sphere is kind of another 90 degree. Yeah, 90. This one is 90 degree. Yeah. So given a phase disk, yeah, we have a phase. We'll start with a 0, and we have a reality. This is a reality. This is imaginary. Yeah, and based on this one, you can see this. The state we have a start from phase. This on 0, right? You got 0. Start from 0. We have a reality. We have imaginary. Start from 0 too. So probability for get 100. Probability for the qubit 1 may up to about 100. Yeah, 100. You can go to the south or you can go to the up. So over here, because the probability for the qubit 1 is account 110, so P is equal to 1. So do you remember over here you can P is probability for qubit 1, right? So if it's 100%, so that is equal to the 1. So here is after you change to the formula. You change the formula P is equal to 1. So you can calculate. You see, this is per C, per C, qubit per C. After you change the P is equal to 1, so you can see per C equal to the qubit 1, right? This formula, previous formula, this one, per C, this per C. And after you change this one to the 1, P is equal to 1 here, and you can see the final value is qubit 1 only. And about the second example, now you can see our qubit change to the about the phase, about the P value. P value that means equal to 180 degree. So the total, this total about this kind of the circle, that is the total 360 degree, right? If a half, that's kind of 180 degree, and this quite 160 degree. And you can see the probability for the qubit 1 can be 50 hundredths, because it can go to the this or you can go to this part. So after you can you see because the probability for qubit 1 is 550, so we can change the P is equal to the the 1 over 2, and after you can change to the qubit per C, you can change one P over there, so you can see over here is kind of the total value, and over here you can see this negative, this matrix, negative. So that is formula for the 2 qubit, this 2 qubit 1 or 2 qubit. And now you can have a kind of general case for the n qubit state. N qubit, when you have an n qubit surface different, actually it's different about this part, and you can see about the pk, you can see this k, okay. You can see over here is we have a k. You can see over here we have a k pk. So this kind of sum, right? The sum for you see the p equal to sum. This kind of sum. This kind of general case when you have n qubit state. The previous example only about the focus on 2 qubit state. Okay, about the when we have just general case, so what about the sums of the common gate? We have a C0 gate, right? We have a NOT, this kind of NOT gate. NOT gate that means we have this line is 1, this, and the rest is 0. So after the value go to through the Q case with the NOT gate, so the NOT gate. And this NOT gate, this one is qubit state, qubit state. And after go to the NOT gate, so you can see this probability for qubit 1 is equal to the 100, right? 100 percentage, or P is I think that this is P equal to 1. And if before the gate is this before the gate is I just mentioned is 0. After we have probability for the qubit 1 is 0, but after gate the NOT, right? So you can see this qubit I just mentioned P equal to 1, right? So the probability for qubit 1 is 100%, 100%, or the probability this one state is 1. Yes, I just mentioned. Now we have 8 gate. 8 gate. If you see over here, we have a negative and positive, and this one is and this one is negative. This one is positive. And the snapshot, when you run about the this one is this is wrong. This one is 8 gate. Okay, this will not get, this is 8 gate. I think this is kind of slide have a kind of little bit wrong. This is snapshot for 8 gate can be solved after you run the Hanama gate, right? So you would see this one is about the equal to the p about the 1.2. Yeah. So this is kind of 50%. Yeah. After gate, you can see this one come from 0. After Hamada gate, we have a reliability is 1, and we have a probability for the qubit 1 is 50%, right? And we have RX gate. RX gate, we will involve to the angle. This one we have this is theta the angle. So if we use a snapshot for RX gate, we can find the matrix, the representation. And if you see over here, we have start from the phase 3 pi over 2, 3 pi over 2, and then you can see this one move. Actually, this one is more like this. That is called the I think this is equal to the 270 degree. Yeah, you can see this is around nearly. Actually, this is over here. Yeah, this is a start point. So this is 3 pi over 2. So the probability for the qubit 1 is 50%, and you can see the result. So about the after you run the snapshot for the RX gate, yeah, this one is a C0, right? And we have a probability. This is, for qubit 1 is about 1. And after we run the RX gate, so we the probability become only 50 degree. And this is how how the calculation appear in practice. And you can calculate use Euler formula. Yeah, Euler formula. And this is kind of the final result. Okay, we already learned about the Euler, so I leave this part for you to recall the practice as previous lesson. So you can go here how to calculate H1. Okay, so today I already mentioned about the one of very famous phenomenon. Phenomenon. It's called a phase kickback, a phase disk, or someone will be call it a phase kickback. So one have a 2 qubit entangled together, so they will change from state. So we and in this lesson I already introduced 2 operation. It's called the C0 and the RX gate can help you to do change form the state probability for the qubit. Okay, thank you and see you next the lesson.